Right, thank you everybody. It's a little late in the afternoon. I'm going to challenge you a little bit and warn you that there are some graphs coming up which you can look at and concentrate on if you want to. If you prefer to stay asleep, I'll just be slightly kind of insulted. Now, given the recent changes that have been happening in the industry, I've changed the title a little bit because I feel I can include Isambard, which is a Cray machine, as well as Catalyst, which is an HPE machine, since those two companies are now kind of walking down the aisle with each other and will soon be very, very good friends, I hope. But that gives a nice perspective on what we've been doing at Bristol in terms of what you can do with ARM processors, whether they work or not, whether they might be useful. And we're very much at the time where we can share that with the community at large and encourage people to join up with us and if they want to try some codes on these new machines. So a little bit of background about the University of Bristol, for those of you who don't know. We've got quite a large academic audience here, so I'll skip over some of this. Bristol is a relatively new university, but it likes to think of itself as historical, at least architecturally, with a lot of Victorian kind of architecture that looks very old, but actually is only Victorian. We've got 18,000 undergraduate students, 6,000 or so postgraduate, and about 5,000 full-time staff, and quite a reasonable annual income for research. There's a nice picture of the West Country. I think I should start charging the Bristol Tourist Board for pictures of the Bristol Suspension Bridge and the Avon Gorge, and those little dots at the top are balloons, hot air balloons, so if you come to Bristol at the right time it's very pretty and scenic. The University of Bristol is a Russell Group university. We're quite research intensive, and that really kind of focuses what we do in HPC at the university. We try and be quite innovative and try and embrace new technology perhaps a bit earlier than many other people would do. Oh, I have that slide twice. Well, there's another lovely picture of Bristol just to show how nice it is. The ACRC Advanced Computing Research Centre is the group I lead at the university. We provide high-performance computing services to the university and also a research data storage facility, and we have a team of research software engineers. The software engineering team is growing rapidly. That's proving to be a very popular and interesting area, which is, I think, both important and quite rewarding, because software is important. It's not just down to hardware. And having new hardware means that you have to think about that software too, which I'll come on to a bit later. We have a number of clusters. One 15,000 core Intel-based one, a smaller 5,000 core system, and now we have a couple of access to a couple of smaller ARM-based ones. We also have a very active computer science group, not as big as Edinburgh's, but quite a large one for a UK university, led by Professor Simon McIntosh Smith. He does undergraduate and master's teaching in HPC. Which is a relatively specialised and rare course to teach in the UK. He also has postgraduate researchers in his group, and he's the PI of the Isambard project, which is the Cray ARM-based system. So the really nice thing is we work very closely with that research group. So the HPC provider in the university is working very closely with people who are teaching and doing research into HPC at the same time. And that gives us a really nice synergy and makes it very interesting, not only for us on the service side, but also for the people on the research side to actually see what real computers are about and see how they really get run. Simon is also the chair of the HPC Executive, which is the governing body for ACRC, my unit. So we have a very strong academic lead on what we do. And the really neat thing is that there are two Simons. So whenever you're trying to contact either one of us, it's just fine because we have the same name. So a little bit of history here. I don't know, Mark, whether you remember, you're probably not quite as old as some of these, but almost.
I remember them all.
Very good, very good. You've probably got one in your attic of each of them, haven't you? In the old days, every vendor made their own supercomputers and they made their own processors as well. And a lot of them made their own memory as far as I can remember. So there are these old names: Control Data, Cray that came out of Control Data, IBM, Amdahl that came out of IBM, Digital Equipment Corporation, famous for their VAX computers, and then some kind of more specialist HPC machines like Convex and the Transputer, the NEC FX, huge vector machines, lots of different ones. And as time went by, a decade, 15 years later, we got a separation between CPU manufacturers and supercomputer manufacturers. And you would get many manufacturers still, but they would buy their processors in from a specialist CPU manufacturer. So there's a little bit of standardization, and there were things like Spark, IBM Power, MIPS, Intel, and AMD. Going on another 10 or 15 years to the present day, here we are, and it's kind of mostly Intel. So congratulations, Intel. You've got a very substantial portion of the market, and certainly most of the HPC side of it. AMD have their ups and downs. We've seen that. Sometimes they're very popular, sometimes they're not so popular, sometimes they have a bit of trouble, sometimes Intel have a bit of trouble. That's the way of the world. Making processors isn't easy. Simon's history is in CPU design, and he's talked about that sometimes, and it's amazing that things actually work at all. So we've got Intel, AMD coming and going, a little bit of Power, but have we got an IBM representative here at all? Oh, good. So my question is, can I buy a Power computer at the moment? I don't think I can I? The Japanese vendors, they're still doing some interesting things, particularly with vectors and their own processors, trying very hard. But basically, that's about it. We don't have much choice anymore. Well, until now. Now, ARM is a company that has a design for processors, designs processors. It doesn't make them, though. It licenses the IP to chip foundries and manufacturers to make the processors for them. And they also provide a lot of supporting tools and services to validate those processors, to make sure they work as expected and adhere to the design parameters. Now, they are extremely widespread. How many of you have an ARM processor? Hands up. Okay, good, fairly sophisticated audience. How many of you have like 3 ARM processors? Okay, yeah, so ARM processors are in your smartwatches, they're in your phones, they're in your tablets, they're in your washing machines, they're in your cars, they're in your future Internet of Things devices. So they're a very well-established company, so it's not like they're real newbies in CPU technology. The interesting thing was the development of a 64-bit design. Now, the 64-bit design is really nice because then we can do the kind of maths we want to do for high-performance computing. So we'd all played around a little bit with ARM processors and also the smaller Intel 32-bit systems, low power. But now we've got 64-bit chip. Probably we can do some real HPC with. So, being computer scientists and university, we were very excited about this. And Simon applied for a project with EPSRC and was awarded £3 million to work with Cray to deliver an ARM-based supercomputer. And that's the Isambard project. But we were quite greedy and we wanted in on anything else that was going on. And the Catalyst UK programme started as well, which is a collaboration between HPE, Hewlett-Packard Enterprise, ARM, and 3 UK universities. That's Edinburgh, Bristol and Leicester. And the primary aim of that was to demonstrate that you could have an ARM-based supercomputer in a real-world environment. Now, you might think a university isn't a real-world environment, but actually for an HPC system, it is. It's like being in the Wild West. You've got students, you've got postgraduates, you've got researchers doing really serious stuff, and lots of egos demanding that things work really well or even better. So, both these projects started and they've been going since about January, and we have multiple ARM-based supercomputers running in the UK now. Bristol is really lucky to have Catalyst and be part of the GW4 consortium, which is the Isambard crane machine. So we've got both of them, and we can compare the two with each other. The systems are running well. They booted up all right. Linux just kind of looks like Linux. If you SSH to it, all those Linux commands are there. They all work. The model number looks different so if you do, HWinfo or something, but otherwise you wouldn't notice it was different. And also a lot of the hardware does as well. So we've got storage, we've got SAS, SSDs, disks, PCI, all that kind of stuff that you might think would be a bit tricky. You've got a new processor, you've got new motherboards. Are all those peripherals and things you stick onto them going to work right? You'd expect things to freeze up, you'd expect to get bus errors and all those nasty things. And I've seen those before in previous generations of computers when they were new, and you'd get systems which would crash 3 times a day. You would get the hardware knocking over the operating system, you get the operating system falling over because of the hardware. But we really haven't seen very much of that at all. It's absolutely amazing. I was really quite surprised. And even on complicated things like interconnects, that's all working as well. So we can build proper supercomputers out of ARM processors, and they stay up and they're running user work. So the software works. We've got a bunch of compilers, including ARM, GNU, Cray, LLVM, CLang and FLang. They all work. They're actually very reliable compilers. Again, in the past, compiler bugs were really quite frequent, and I've debugged compilers myself in the dark ages. Most of the compilers work really well. Some of them have a bit of a problem doing some optimization, but they all generate good codes, and they can compile most of the code that you throw at them. So sitting down, compiling your 200,000 lines of Fortran or whatever it is, these compilers can just chew it up, there's no problem. And the executables run. And they give the right answers. 3 big ticks. Performance. Okay, so the performance must be rubbish, right? Because everything else going so well. This is too good to be true. So the processors that we have are the ThunderX 2, which were built by Cavium, who've been taken over by Marvell. 32 cores per socket, so 2 sockets per node gives you 64 cores per node, which actually was quite fun because at that point they were by far the largest number of cores we had per node on any of our systems. And a bit more memory bandwidth, 4 memory channels instead of 3. The clock speeds are a little bit lower than some of Intel's best, but the performance per node seems to be pretty comparable. They're not deadly slow, they're not blindingly fast, but more or less the same. Now here's a few little tech specs. So these are picking some very nice Intel processors. When we were doing comparisons, we wanted to make sure that we picked kind of the best of breed that we could. There's some things with the power there and the bandwidth, and there are some list prices for processors, just so you can bear that in mind as well. So the performance is the interesting part. What can we get out of these machines? We picked 4 benchmarks, I selected 4 benchmarks here, which are one of the number of which we've run, simply because they're different examples of codes with different characteristics. Probably everybody here knows what these are. There's GROMACS, which is molecular dynamics, finite difference package, OpenSBLI, VASP, which is an atomistic scale and materials modelling, and OpenFOAM, which is CFD. So here's the graphs. So go to sleep, those of you who want to go to sleep. Those of you who are interested. This is a comparison of the list of previous processors there with the relative performance compared to a Broadwell rated at 1. And on the right-hand side, there is also a graph showing the parallel efficiency when you scale up to 16 or 32 nodes. So we're doing an individual kind of node measurement, and then we're looking at scalability. So both the right-hand one is more HPC related, the left-hand one is more or less down to the processor capability. So you can see that the Skylake does really well on there, the green one, that's really high. And some of the figures for the catalysts, the purple one and the dark red one, well then it's kind of half, so half the speed. It's not brilliant. Some of this is down to tuning. Some of the applications have some intrinsics in them which use the Intel vector instructions, which mean they go quite a lot faster. We haven't got those on the ARM processors yet. But I draw your attention to the slope on the left-hand graph. Look at how the TX2 and the on Isambard and Catalyst get better performance improving performance compared to Intel as you go on to more nodes. Now that's most likely because you're getting that extra memory bandwidth, and as you scale up the problem, you get more and more memory bandwidth to work on that problem at one time, and that's where the performance is coming from. So that's an interesting characteristic where on a couple of nodes it's not so good, but as you scale up, the performance is approaching that of the Intel. So this is OpenSBLI. Now this is kind of the other way around. This really rather favours the ARM processor, and this is because of memory bandwidth, and at a very small scale it's much better, and this code really just relies mostly on memory bandwidth. It's surprising how many HPC codes do that, but when you think about it, we're doing matrix multiplication a lot of the time, or we're doing FFTs, and we're moving a lot of data around, and when you reach a certain scale, that needs to go out to memory. If you're lucky and it's in cache, then it's a different ballpark. But if you've got large-scale problems with larger arrays, then it's the memory bandwidth that's really an important characteristic for these kind of codes. Here's VASP. VASP is highly optimized, and there's some really good tuning being done in there by the maintainers of that package, and it really, really goes well on that Skylake 28 core. That's super performance. In time, perhaps the ARM performance would go up a bit with that same kind of tuning applied to it, but it's not, it's not a rubbish performance. It's kind of 75% on one node, a little bit less on 16 cores, on 16 nodes. So perfectly workable performance. OpenFOAM, again, that's a CFD code. Performance is bearable. I wouldn't necessarily reject that. And if you go back to looking at the first chart, if the price of the processors is much less than the Intel, then on a cost performance level, you might choose to have that for your HPC system rather than the more expensive processor. So we've got our efficiency and performance calculations, but we've also got our money to consider as well. And as you know, we don't have that much money, so we have to spend it very wisely. So here are my conclusions. ARM is capable of doing HPC. I think we've demonstrated that. We've done it with real-world runs. We've got decent performance. We've done it on 2 different systems from 2 different suppliers. The results are correct. We've done real science on them. Some of our researchers have transferred some of their research projects to the Catalyst and the Isambard systems and are doing proper research, which is in the course of being published. So I think the major CPU supplier might have a little bit of competition, which is good, I think. Everybody needs a bit of competition because we don't want to get a bit kind of stale on board. So moving on from this, I'd like to port more code to ARM, do some more performance measurements, prove that more applications work on the systems. All of the Catalyst and the GW4 group welcome applications from other universities, research establishments, and industry, commerce, ISVs. Really would like to do some more work on some commercial codes so that we can prove that they run on these systems. Each of the universities on the Catalyst program has slightly different areas of expertise, so feel free to contact any of them, and we'll find somebody who knows something about what you're doing and can help you with that code. Kind of stay tuned, because I think this is really exciting. This is the first time we've had a really new processor on the HPC, in the HPC game for a very long time. So I'm quite excited about that. And just because this is an HPC talk, here's some computer pornography. I've taken the covers off. Can you guess which one is which? So the one on the left is the catalyst machine at Bristol, and the one on the right is the Isambard system, the grey one. So, just about on time. Any questions, please?